Hello everyone, this is Wang and welcome to my presentation. Today I'm here to talk about our work, EarDynamic, an ear canal deformation-based continuous user authentications using in-ear wearables. This is joint work with my advisor Dr. Zhang and my colleagues. Let's begin with some background information. The ear wearables, outside earbuds, has become the most popular wearables nowadays. This includes AirPods, the headphones, and the wireless earbuds. Let's look at some numbers here to see how popular they are. The AirPods revenue in 2019 reached $12 billion, which means it's really making a lot of money, and only the revenues of the AirPods are more than some of the top technology companies such as Dolby, Nvidia, AMD, and Spotify. The AirPods has its unique advantages. Besides the traditional functions of the earbuds, such as talking with friends, listening to music, they're also natural for ubiquitous computing, such as it's quite convenient for hand-free scenarios to issuing voice command. It could also enhance the user experiences of some cutting-edge applications such as VR and AR. So since the ear wearables has so many advantages, how do we utilize and sense the novel biometrics? And in this work, we aim to utilize the biometric of ear canal to provide continuous and transparent user authentication. Traditional biometric authentications, such as fingerprint, face, iris, and voice-based are all popular authentication methods. However, they all come with weakness, like the fingerprint is vulnerable to spoofing attack, and face-based authentications may not work well when our face is covered. And the biometric of ear canal has some advantages compared with the traditional ones. First, it's more secure, and it could provide a continuous authentication and is transparent to user. And when we utilize dynamic deformation of the ear canal, it becomes safer because the static geometry of the ear canal is more vulnerable to spoofing attack compared with the dynamic, and it's more secure because dynamic deformation will impact the accuracy. Let's take a close look at why the biometric of ear canal could be used for authentication. There are two scenarios for our ear canal, the static and dynamic. Let's first look at the static one. The static geometry of the ear canal has diversity over the different subjects, and diversity could be attributed by three aspects: the interspace of the ear canal, the curvature and the cross-section of the canal, and the composition of the ear canal wall. Ear canal could also be dynamic, because our daily activities could make the ear canal wall moves. In that figure, when the people are speaking, that is mouth motion include both jaw and tongue motion, will make the geometry of the ear canal change, and this is due to the TMJ attached to the ear canal wall moves. And similarly, the strongest neck muscles attached near the ear canal, so when we are moving our head, it will also impact the ear canal. And in our work, we find that the dynamic of the ear canal has individual differences and could be used for user authentication. So the next question is, how do we measure the dynamic? As the ear canal deformation is invoked by the movements of the head and the articulators. So for the head, it's pretty straightforward because we could utilize the motion sensors to measure the head motion. And when the user is speaking, for instance, the jaw, tongue, and the mouth are moving, and we could categorize this deformation by measuring various articulator gestures. But these measurements usually require multiple specialized devices attached to the articulators, so which are impractical here. To solve this technical challenge, we rely on the phony pronunciations. In particular, each phony pronunciation corresponds to a unique and consistent articulator gestures. By grouping the phonies with similar articulator gestures, we are able to group the corresponding ear canal deformations. So this figure illustrates the articulator phonetics corresponding to the various positions of tongue and jaw here, and these category results are summarized in this table. We have the 7 categories of the ear canal deformations. So after we categorize the deformations, we could utilize them. Let's take a close look at the details of the static and dynamic scenarios. So for the static, when the user wears the earbuds and send inaudible signals to record the reflections, we could extract the channel response as the green line shows here. And for dynamic, when the jaw and the head is moving, the ear canal wall also moves. Thus, the geometry of the ear canal differs, just as shown in this figure. We could then extract the channel response, and as shown in the brown one here. When the geometry of the ear canal deforms, its dynamic acoustic features also change compared to its static features. And then, dynamic deformation features are extracted based on different phonic categories for authentications, with then boosting them into one strong classifier for user authentications here. And this is our prototype hardware used in and details of the data collections here. And here is our results. Based on our evaluations, our system could achieve overall accuracy of 93% across different environments and the participates. And this is our conclusions. Thank you, and any questions?